Hey, I wanted to share a video that goes through a pumping problem where we set up the orientation differently. So this is a modified version of the slide we had in class today, but the way that we're computing work is force times distance. We have mass, which is rho times volume, times the acceleration due to gravity, so that's mass times acceleration, that's a force. We have the distance that the water that we're pumping out needs to travel to get out of the tank. And so that gives us the work done, force times distance. So if we sum up all those WKs and take a limit, we get an integral where A to B is where the water exists that we're pumping out of the tank. And we have the force times the distance. So this distance function will be different depending on the orientation we do, and the variable of integration may be different depending on if we use a different variable. So let's look at setting up this example question with different orientations of axes. In class, we did one where 0 was at the top of the tank and the positive x direction was down. Let's do something different this time. Let's start where right here will be x equals 0, and then we can have the positive x direction go down. So from the information we have a radius of 4, we have a depth of 8, so down here we'll be down at 8, x equals 8, if we keep that axis going. And if we go up to the top of the tank, that's at x equals -2. Okay, so we need to figure out if we're at some slice of our water with some little thickness delta x, and that's at some height x, what's the distance that the water needs to move to get out? The water needs to start at x and be brought to x equals -2. So as we've always done, our distance, we take the larger thing minus the smaller thing to find the distance. And since our positive x direction is downward, our larger thing is the x. So we have x minus -2, which is x plus 2. So the distance that the water needs to move out is now x plus 2. The reason this is different than what we saw in class is that our origin is now moved to be at the water level instead of being at the top of the tank. So if we want to set up our work integral, we also need to figure out what the volume of a slice is. So at some x or xk, our volume is pi r squared delta x. So the area of that circle times the thickness. And our radius is always 4, so we have pi times 4 squared times delta x. That gives us our volume. So our work integral is from somewhere to somewhere. We'll figure out the limits in a second, but we'd have the density of water times the gravity acceleration times the volume, which we've now figured out is 16 pi, and then the delta x becomes dx, and then our function that represents the distance, our distance function, d of x, is x plus 2. Now, what are the limits of integration? If we're doing part A, then our limits of integration to pump out all the water, well, the water height goes from 0 to 8 in the positive x direction, so our limits of integration are from 0 to 8. If we were going to write this same integral down for part B, we'll do that in green over here, our work integral would be from 0 to 4, which is half of the depth of water, so 0 to 4 meters, of the same thing. The density of water, gravity constant, 16 pi is that area of the circle, dx gives us a thickness for volume, and x plus 2 is the distance that the water would need to move to get out of the tank. So that's a variation on what we'd seen in class. Let's do one more variation where we put 0 at the bottom. What if we put 0 at the bottom and we have the up direction be positive, and this time also let's have the up direction be y, and it's positive in that direction. So what that means is we're down here at y equals 0. the water level is at y equals 8, and the top of the tank is at y equals 10. So what's going to change? Not a ton. Any place at some yk in our region, we will have some piece of water that looks like a circle with a little bit of thickness. So our Vk is still pi r squared delta y. Now we've changed our variable name to y. So we get 16 pi delta y, because our radius is still 4. Let's think about our distance function. It's now going to be a function of y, and what is the distance that at yk we need to move? Well, the distance at yk that we need to move is to move from yk up to y equals 10. And notice how I said up to. We still think of up as up, away from the center of the earth, but now our variable positive axis is also up. So we take the larger quantity, 10, and we subtract the smaller quantity, which in this case now is y. So our integral will have a different distance function, and we will likely have different bounds of integration. So let's see what we have. So we have our work integral would be equal to, and let's talk about the limits of integration in a second. We'll have the density times gravity times the volume, 16 pi dy, times that distance function, 10 minus y. Now, what is the limits of integration that we need to use? We need to pump out all of the water. All of the water, so if we do that with blue to talk about part A, all of the water is represented by 0 to 8. So that doesn't really maybe feel strange or different to us than what we saw previously. We're just covering the entire width of water from 0 to 8. The difference is when we're pumping out half the water. We're actually going to pump out, say, like the top half down to y equals 4. So our limits of integration for that one would be from 4 to 8 of all the same things. Density of water, rho, g, the gravitation constant, 16. Oh, I'm realizing I forgot my pi over here. I think I said it, but forgot to write it. We've got a dy, and then again, that distance function, 10 minus y. So the way that our limits of integration are different is we need to think about that the top half is the half that's going out first. So the top half is taken out first, so our top half is represented by y equals 4 up to y equals 8, whereas the entire tank being emptied is from 0 all the way to 8. I hope this helps a little bit with giving you some alternative ways that we could set up a coordinate system for dealing with pump problems.